energy. So basically, like we have a force, right? Force of gravity times m1, m2 times the gravitational constant, big G, over r squared. And because it's a force, that means it could also do work, which is defined as the change of energy. But in this case, you're going to be changing the gravitational potential energy, like say if you go farther away. So work is also defined as integral of force times dx. So basically what I'm going to do is I'm actually trying to find the work done by gravity to determine the gravitational potential energy for orbits. So we're going to have the bounds, so that's r to infinity. Because we're going from very small amounts, we're trying to go from very, 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 very small amount of work to the energy that we can go up to for the distance now. Like, say, what I'm trying to say is if the distance between the two like objects are infinitesimally small, we're gonna try to spread them apart to distance r. If that makes sense. So, and because r is a variable here, it'll we're gonna have to choose a different variable here to when we're integrating. So I'll just use x squared times dx because this will mess with the bounds and such. So when you're integrating, in this case, since we're integrating with respect to x, g, m1, and m2 are constants, so we can just take that out. So g, m1, m2 times infinity times r 1 over x squared dx. So I'm going to have a little scratch work. So if we remember the reverse power rule, so let's rewrite this as x to the negative second. You add 1 to the power and divide by that new power. So this simplifies to g m1 m2 over x, because this will just simplify to negative x, negative 1 over x, because negative 2 plus 1 is negative 1. So, and here's a negative right here. And this is being evaluated from infinity to r. So we get g over m1, m2. So over r. And then this is our final energy, right? E, F, or U, G, F. And then we minus the initial energy, so G, M1, M2 over infinity. So basically what we can do is when we take the limit as, like, say x goes to infinity, of negative g m1 m2 over x, let's just take an example. 1 over 10 is 0.1, 1 over 20 is 0.05, and then so on and so forth. It gets smaller and smaller and smaller. So when you get infinitely small, it will get closer to 0. So basically, this part is no more. And then we get the work done, or in this case, the gravity, because the potential gravitational potential energy, because there's no change in energy, or at least there's the change in energy is defined as the gravitational potential energy. Just like how, like if you're trying to find a network and you're initially at rest, the network would just be the kinetic energy. So basically, the gravitational potential energy is negative g times m1 times m2 all over r. This looks very similar to what force looks like. So make sure not to get them confused. And also make sure this is always negative. So yeah, we can actually apply this to conservation of energy. So let's draw like an orbit right here. So like here's like a sun, and then here's planet 1, and then here's planet 2. So planet 1 is a lot closer to the Earth than planet 2. So that means it would have a much smaller gravitational potential energy. I mean, yeah, so it'll have a much smaller gravitational potential energy, which means that it will basically um, have more kinetic energy the closer it is to the sun. And then when it's much farther out, there's less kinetic energy, but more gravitational potential energy. So when you're applying conservation of energy, remember that 1/2 mv squared minus, remember, because gravitational potential energy is minus in this case, m2 times m1, and this will be m1 because we're talking about the object that's in motion, over r, would all be equal to 0. But and then this would be our initial. But the thing is, in order to be considered conserved, this would have to apply to the final state as well. And because both of these equal 0, you can set them equal to each other.